Hi, welcome back. In this lecture, I want to give you a brief and general overview about programming quantum computers. In this course, we often talk about QPU or quantum processing units. One important point to realize when working with the quantum computers is that a quantum computer is not really a general computer, but is more a coprocessor or accelerators. It turns out that today a traditional computer uses a wide variety of coprocessors, each suited for different specialties. So for instance, we can have a device that is very strong in making floating point arithmetics, or we can have a device that is very good for signal processing like a DSP, or real-time graphics like graphical processing units or GPUs. There are some accelerators that you might know. For instance, I talk about GPUs that are graphical processing units that are very good for graphical workloads. You might heard about Google TPU that are specialized processing units for machine learning. So the T stands for tensor processing units. And some of you also might have heard about FPGAs that are yet another accelerators. So what are the characteristics of accelerators, for instance, like the QPU? Well, the main characteristic that they always need to have an host. An host is a classical computer. So quantum computing today exists only if there is one host that is classical. So it's very important to realize that the quantum computing system is inherently a hybrid system where we have a host that is a classical, and then we have a QPU that is our quantum processing units. So we're going to offload our program to the QPU and from the host to the QPU, and then we are going to retrieve back what are the results of the measurement or the observation of our QPU and get back to the CPU. So in this picture, you have an example of the system of the quantum computer at Rigetti companies. You see here we have the so-called host, that is the traditional computer, and then we have our accelerator QPU that is here. It's actually just below here. All this system is actually used to cool down the system to almost 0 Kelvin, as we saw in the previous lecture when we talk about the superconducting qubits. As I said in the previous slides, quantum computing is really a hybrid classical quantum computing. In reality, we are here as a user. We make our program once that is expressed as a combination of different gates, and then we send to the QPU, or we offload. That is the specific term that we used when we deal with the accelerator like GPUs, in this case QPU. So we offload the code. At this point, once the QPU has the code, it can execute it. When it's finished, we retrieve back the results to the CPU for further analysis. To program a quantum computer consists of 4 steps. First, express our program as a quantum circuit. That means that we are going to define a combination of quantum gates acting on the qubit. The second step is to offload our code that is actually defined as a combination of quantum gates to the QPU. The third step is actually the step that is only executing on the QPU, that we call preparing the distribution. Right? So we have our qubits, and then we deal with the superposition, and then the last step, we actually measure, so we collapse the superposition of our quantum system, and we retrieve the measurement or sample the distribution if we make many measurements. So let's look at step 1 and 2. So the first step is actually to express our code as a combination of gates. So we'll see later on so-called the quantum gates, but we're going to express our code as a combination of different gates. So for instance, here we have X acting on the first qubit. So X we will see that is the NOT gates. And then after we take the results of these gates, and then we make an operation so-called control NOT operation. And we can express our algorithm as as a workflow of different gates, right? So this is very, very interesting how we're going to express our program. But don't worry yet. We will learn how to express our algorithm using quantum gates. After we express on the CPU our code as a combination of different quantum gates, we are going to offload this quantum circuit to the QPU. So we're basically sending to the QPU. So one interesting fact is that somehow QPU and FPGA are quite similar. So the closest classical accelerator to QPU is actually the FPGAs. In the same way that we provide a circuit to the QPU, FPGA work very similarly, in the sense that we provide a circuit to the FPGA. In the case of FPGA, the circuit is classical, right? So it's not quantum. But there are some similarities between FPGAs and QPU. QPU and FPGAs are both accelerators, and the way to express a program to be run on the accelerator is by expressing the circuit, our algorithm as a circuit. The third step is actually only working on the QPU, is basically running our algorithm that is basically running our quantum circuit. The last step is actually to provide the measurement. So we can make many measurements. That means that we are actually sample the distribution. So we measure many times, we run the circuit many times, and then we measure what is the measurement of our qubit or multi-qubit system. Sample the distribution and then send back the results to the CPU. What are the characteristics of QPUs and in general of accelerators? Well, usually a program running on a CPU will issue QPU instructions and later retrieve the results. So this means that we are issuing quantum gates and quantum circuit, and then we run on the QPU, and then later on we retrieve the measurements. It is also true that some tasks are very suited to the QPU. You will see later on in the course which kind of algorithms are very suited for quantum computing. Obviously, we need algorithms that can take advantage of superposition, but there are some other tasks that are not convenient. So they are going to run slower on the QPU, on the CPU, or in some cases, they cannot even run on the QPU. What is important to notice that accelerators and QPUs runs on a separate clock from the CPU and usually has its own dedicated hardware interfaces to external devices, such as, for instance, optical outputs, and then there are buses connecting a different system. A typical QPU, but also accelerator in general, they have their own memory, which the CPU cannot really efficiently access. So there is quite a lot of memory and data movement. And the last point is that when a computation is done, a projection of the result is returned to the CPU. That is, we make a measurement of our qubit system or multi-qubit system. And most of the QPU internal working data is actually discarded. So we collapse all the superposition states. It turns out that today the easiest way to access a quantum computer is through a cloud. Cloud quantum computers make it possible to run quantum algorithms on a real quantum hardware. And development libraries that are on a quantum cloud, cloud providing quantum services, enable this capability. Access to some quantum computing system is freely provided in many cases via the cloud. For instance, the IBM Q, the Google system, the Rigetti system are accessible through the cloud. It turns out that in many cases we don't actually need a real quantum computer to run. Obviously, it's very exciting to run one, but for debugging reason or for a training reason, it's often more convenient to run on a quantum computer simulator. Turns out that many quantum computing frameworks, they also provide a quantum computer simulator, and we're going to use them for debugging reason and developing our quantum code. As soon then we have the final quantum algorithm that is fully debugged, then we can run on the real quantum computer. So to test our code prior to running on a quantum computer, most of the quantum computing frameworks provide a quantum computer simulator. that runs on actually on a classical computer. So it can be our laptop, for instance. IBM, Google, Rigetti provide quantum computer simulators when we install their frameworks. We will mostly use quantum computer simulators in this course, so we'll save the credits on real quantum computers for doing maybe the project or something that we really want to run there. And one part one interesting part when working on a quantum computing course is also think about developing a quantum simulator yourself. So definitely to develop a quantum simulator is really very fun final project for the course. So what are the limitations of a quantum computing simulator? Well, obviously there are some limitations, otherwise we wouldn't we develop on a quantum computer. Well, the major limitation is really the so-called exponential explosion of classical memory. There are numerous techniques to classically simulate quantum circuits on the quantum computer. But what is this exponential explosion I'm talking about here? Well, the major limitation is that to store the most general of an n qubit system, for instance, we have n qubits, that we will need all 2 to the n complex number of the system wave function must be stored on the classical computer. In practice, on a regular laptop, this is extremely challenging. Already we can, maximum go up to current laptops, to 20 qubits quantum computers. You can try with quantum simulator. You will see that to run already on 20 qubits will take quite a lot of time and will put a lot of pressure on the memory of your laptop or your workstation. So if you look at the number, if we have 30 qubits, we try to simulate a 30 qubits system. When it comes to the memory, we will need roughly a gigabyte. So it's still feasible, but it's quite challenging. If we go to up to 40 qubits, we will need a terabyte of memory. If we go to 50, so not much farther from 30, we will need a petabyte of memory. So that's something you need already here, a super computer to do this kind of simulation, because you need a lot of memory. So these memory requirements are already reaching the limits of today's best supercomputer, even for a rather modest number of qubits. So 50, 60 is quite small number of qubits. Larger system cannot be simulated, since they wouldn't have enough memory to write the wave function. So if we want to keep track of what is the superposition, so the cause complex amplitude, we won't have enough memory on our largest current system. So this is the last slides, and talk to you soon.